Well, here we are again, and thanks for joining me. I'm going to talk briefly now about how we could turn something like this thing on a page into a trig function. And we're going to pretty much combine everything we've talked about in the last couple of videos to bring together an understanding of the important features that you can visually see on this graph and how they relate to the A, B, C, D, or the different components of a sine or a cosine graph. So let's do this. So let's talk about some of those important features that we talked about in video 1. Now in video 1 we identified that first of all we had peaks and troughs. So I'm going to make a little note up here that my peak equals 3 and my trough equals -1. Now of course I'm talking about the y values here, I'm talking about their heights. There are multiple x values for the peaks and troughs. As you can see here I'm marking all the trough ones. So I'm not considering those just yet, just the y values. That's my peak and trough. And I also talked about the midline, so where the middle was. And in this case, you can see that the midline is here. That might be a little bit hard to spot visually to start with, but you will get there, I promise. But we call that the midline or the center of equilibrium, and it's equal to 1, or y equals 1. So my y value is 1 at each point there. So there's our midline, peak and trough. Now they're our vertical things. Let's talk about our horizontal things now. So the last thing we talked about in that set of videos, the different things that were happening, were the period. So that's a period, but this is also a period. Periods are peak to peak or trough to trough. Or if you are going from a peak to a trough, that's half a period. Or if you're going from this peak to this trough, that's 1.5 periods. So it really depends on the graph you've got. You may only have half a period to work with. In that case, you have to recognise peak to the trough or the trough to the peak is only half a period. You can also use from a midline that's going upwards to the next midline that's going upwards. That's also a period. You can see that each of these is the same length, by the way. Just have a look at them. So what I'm going to do is determine the gap between them, and I can see that this starts at pi over 3 and goes up to 4 pi over 3, and so therefore my period is equal to 4 pi over 3 minus pi over 3, which is equal to 3 pi over 3, or just pi. That's my period. So that's interesting that I've got a nice even number there, but it's just a difference calculation. It's what you learn in primary school about subtracting. It's got a few pi's, but as long as you can do some subtracting of fractions, or if it's you're working in a tech active exam, you could always just tech active it. The other option you've got, of course, is that you could go from the y-axis to the next same height position, which is here. That is the low point there heading down, and this is the low point heading down, and you can see that happens at pi. And so there's another way of getting your period, which might work, might not. You have to choose, and you have to be adaptable depending on the question and what's given to you. The last important piece of information was the phase shift. Phase shift, and we talked about the phase shift being how far the function had moved from its standard starting point. So I'm going to talk about sine predominantly today, but there's a good reason why we'd probably actually use cosine more often, which we'll get into. I'll probably talk about it a bit more in class, but for now let's just model this with sine to start with, and we might, if we've got time in this video, come back and model it with cosine as well. So my phase shift for sine is from the y-axis to my first central point, midline, going upwards. And you can see that that's at pi on 3, so my phase shift is equal to pi on 3. So my one notice has slipped down there. There we go, pi on 3. Now, we did talk about one other feature, and that was the amplitude. And it's not the thing that's definitely the most easily identifiable straight from the graph. So that's why I really haven't talked about it here. But it's going to be really important for the function, and it might be identifiable straight from the graph. I can see that it goes from 3 to 1, so the amplitude is 2. I'm going to write this down up here. Amplitude equals 2. So that amplitude is the gap between the peak and the midline, or the midline and the trough. So this should be 2 as well, and I can see that it is. So you might be able to identify it, and if you can't identify it, it might be in halves or thirds or something else, and it's not easy just to pick out. Well, if you know your peak and trough, peak minus trough, which in this case is 4, and divided by 2, because this is 2 amplitudes high. Or if you know your midline, peak minus midline, or midline minus trough will get you your amplitude. So just keep that in mind. Now, your amplitude technically is always positive, although where we place it in a function, it might be negative for certain reasons. But for now, consider the amplitude should come out positive because we're choosing our phase shift based on very specific procedures. And you'll see more of this as we move forward. So there we go, amplitude with a dot over the I. We've got our 5 main pieces of information. How do we turn this into our standard function y equals a sine b x minus c plus d? Well, you remember first of all that the amplitude was the stretch vertically. The a value is the stretch vertically, which happens to be the amplitude. So the a value for a standard function goes up to just a 1. So it just goes up to here and comes back down, doesn't go right up to the top. But in this case, you can see it's been stretched, and you can't see me now, but I'm doing that stretching movement with the hand, pulling something out. The graph has been stretched by a factor of 2. So I can see that a equals 2. The amplitude is the a value. And this is where you might pause the video and start to paraphrase this in your book. You want one big diagram that tells you what A, B, C, and D are. So let's do D next. D was the vertical translation. Well, this thing starts on the x-axis as a center at the x-axis and now has a midline of 1. Well, then D equals 1. And that is my midline. So the D should be the midline value. And then the A is the amplitude, which gives away your peaks and troughs quite easily. So there we go. Now our C value, we'll go to our C value now. Our C value was the horizontal translation, how much it has shifted. And we explored the horizontal translation through our phase shift here. That was when we talked about how much it had moved. So our C value is equal to pi on 3. That's our phase shift. Now I've left B to last for a very specific reason, because it's the only one that's in any way at all slightly complicated, and it's not really, but you've got to do a calculation in here, so it's tiny stuff. Remember our B value was our horizontal dilation. It was the compression or expansion factor, okay? Now, what changes when you compress or you expand a cosine or a sine function? Well, it's the period that changes. And see, if I compress it, it's going to be this orange bar here that's going to get smaller if I compress it or larger if I expand it. Now remember, we said our standard function had a period of 2 pi. This function has a period of pi. And what that tells me, from my knowledge on this, is that B is equal to 2. Because if it's equal to 2, that's a compression factor of 2. Remember, it works opposite to what we expect. So our B is equal to 2, and this is our period. But it's not really our period, because our period was actually pi. So I'm going to show you now a very specific relationship between B and our period. And for this, I'm going to call our period T. And don't ask me why. It's just what it is. We'll talk more about it in class. But our period is T, and the B value is equal to 2 pi divided by T. If you work out how many periods in 2 pi, that will tell you what the compression factor was. So our B value is 2 pi over T, which in this case was 2 pi over pi, which gives us 2. And so we have y is equal to 2 sine 2x minus pi on 3 plus 1. Now, if I just scroll down here, you'll see I've actually screenshotted the thing that I did in Desmos. There's the function. There's the thing we've just found. And you know what? Take a step back for a second and think about it. It wasn't actually that hard. Really, you just get the function, you pull out those 4 pieces of information, and you can create the function that drew that sketch. So let's have a look back up here. I would suggest that you get this thing, maybe without the exact values at the bottom, and you paraphrase that and you stick this thing in it so that you've got that information as well. That's all you need to know about sketching functions. So there you go. That's how we sketch functions and how we determine the algebraic or the function representation of those sketches in periodic form. All the best.